This is section 1.6. We're talking about posterior probabilities, or in other words, Bayes' theorem is what you'll usually heard it called. So let's see. It's estimated that 6% of the American population has the HIV virus. A diagnostic test is used to attempt to detect whether or not a person has HIV. According to historical data, 99.9% of people with HIV receive a positive test result when the test is administered. We also know that overall, people get a positive test result 1.6% of the time. So it sounds like we're talking about HIV, whether or not you have HIV, whether or not you're positive. Okay, and let's see. We also have 99% of people with HIV receive a positive. That sounds like a conditional probability. So let's write down everything that they gave us. Let's see. So 0.6% people have HIV. That sounds like just a plain probability of HIV. And it's 0.6%, so the actual probability would be 0.006. We always prefer to work in fractions or decimals, not actual percentages. Let's see. According to historical data, 99.9% of people with HIV receive a positive. So that sounds like we know they have HIV and we want the probability that they're positive. So that would be 0.999. And the probability that overall people get a positive test result, so just probability of positive, is 0.016. So what is the probability that an American has the HIV virus and they get a positive test result? That actually sounds very important. Well, actually, never mind. I'm going to say that on the next one. Okay, so we want HIV virus and a positive test result. So and means intersection. So if you want to find an intersection, you always start with a conditional probability. This is the only conditional probability we know. So let's use that one. So positive given HIV times the probability of what was given, so HIV. Let's see, so 0.999 times 0.006 gives me 0.005994. Now, what is this in words? This would be of all Americans. Let's see. Let's change that to percentage because we think better in percentages. 0.5994% have HIV and get a positive test result. So that's quite a few. Now, of course, our test isn't perfect. Sometimes people with HIV test positive, and 1 in 100 people without HIV get a positive test result. What we would really like to know is the probability that a person has HIV if they get a positive test result. So this was a new piece of information they were just telling us. 1 in 100 people without HIV get a positive test result. So that would be quite scary for them, I'm sure. Okay? You don't like being told you have HIV if you really don't. But what we want to know here is, okay, so if you get a positive test result, what's the probability that you actually have HIV? So if we know that you have a positive test result, what's the probability that you actually have HIV? That sounds like it'd be very important, right? You took the test and now you want to know, okay, was that actually accurate? Do I actually have HIV? So we want to find a conditional probability. You always start by doing the probability of the intersection. And then you divide by the probability of what was known, which is that you had a positive. So we have all these probabilities written up above. So the intersection is 0.005994, and probability positive is 0.016. Divide this out and you get 0.374. Might not have been what you were actually expecting. So this says, if you get a positive HIV test result, there's only a 37.4% chance you actually have HIV. This is kind of an interesting phenomenon that happens when you have a very rare condition. Okay. But it's also an important thing we also want to check whenever we have test results is you say, okay, we know the probability that you get a positive if you have a condition. But if you get a positive, what's the probability that you actually have that condition? So you want to kind of swap the direction of the conditional probabilities. So let's look at what we did here. We started with the probability of positive given HIV, and in steps 2 to 3, we found the probability of HIV given positive. So positive and HIV, probability of HIV and positive, we again just switched the order of those conditional probabilities. What we did is we found the probability of the intersection over probability of positive to find that conditional probability. Okay, and then, but the probability of the intersection, we had to use the conditional probability times the individual probability. Okay, so what happened is we had a Reverend Thomas Bayes in the 1700s discovered a shortcut formula. And so it's useful when we know one conditional probability, but we're interested in knowing the reverse conditional probability. So this is our official Bayes theorem. Probability of A given B is you'll start with the other conditional probability times the probability of what was known there and divide by the probability of what you know and what you're actually looking for. So notice these two are the ones that match. And then you divide by your other probability. Let's try it. So there is a rare subspecies of beetle, 0.1% of the entire population, that usually has a specific pattern on its back. In fact, 98% of the rare subspecies of beetles has this pattern. Unfortunately for the entomologists trying to classify beetles, some of the common beetles also have this pattern. Overall, 5% of all beetles have this pattern. So it sounds like if 98% of the rare species has this pattern, you think, okay, if I see this pattern, that means it's going to be that beetle. But it might not be the case because other beetles also have that pattern. Okay. So it comes down to what are we looking for here? If an entomologist finds a beetle with the pattern on its back, so he says, okay, I know we have the pattern. What's the probability that it is that rare subspecies? So that's what we're looking for. That's our whole goal. Let's write down the information they actually told us though. Let's see, there's a rare subspecies which is 0.1% of the entire population. So the probability of rare equals 0.1% or 0.001. Let's see, 98% of the rare subspecies. That sounds like a kind of if statement, or it's saying if we know that you're the rare subspecies, the probability that you have the pattern is 0.98. Okay, so if we know you're rare, you have a 98% chance of having the pattern. Let's see, 5% of all beetles have the pattern. So overall, the pattern is 0.05. Okay, now that I have all that, let's go back to what we were trying to find. Now remember, Bayes' theorem says probability of A given B is you'll switch and do the other conditional probability. Now times by the probability of whatever is here, these two will always match, and divide by your other single probability. So let's try that here. So we want the probability of rare given pattern. So this will be, switch the conditional probability. So pattern given rare times whatever you wrote here, so probability of rare, make sure those always match, then divide by your other conditional probability, which would be pattern. Okay, and we have all those written up above. So pattern given rare was 0.98, the rare was 0.001, and the pattern was 0.05. This gives me 0.0196. So even though almost all of the rare beetles have this pattern, it tells us if you find a beetle with the pattern, there is still only a 1.96% chance that it is the rare subspecies. So in this video, we're in section 1.6, and we want to talk about the general Bayes theorem as well as do one more example of Bayes theorem. So first we start with the law of total probability. So let's start with a partition A1 A2 up to AN of the sample space S. So when we talk about a partition, it really just means you've divided up into a bunch of events. So like this would be your first event. So you have an event here, and you have an event here, an event here, an event here, and so you just divided S up into a bunch of different events. You've just divided it up. Okay. Now let's consider an event B. Okay, so here's my B. And what if we wanted to find the probability of B? And we don't know just that. Well, what you could do is you could figure out, well, what's B intersected with this little piece of A? And what's B intersected with this piece of A? And this piece of A, this piece of A, this piece of A, this piece of A, etc. So how can we find the probability of B? We could find the probability of the intersections of B with each AI, okay, and then add them up. So again, you find the probability of each of these little pieces, which is really B intersected with that A piece that's behind it. So the law of total probability says if A1 through AN is a partition of the sample space, then the probability of an event B is probability of A1 intersect B plus probability of A2 intersect B plus probability of A3 intersect B, etc. Or instead of doing intersections, you can find the probability of A1 intersect B by doing the probability of A1 times the probability of B given A1. You can use those conditional probabilities. Now that sounds really complicated. I would never expect you to use this formula by using the formula. Instead, you'll just keep doing what we've been doing, drawing the tree diagrams, and you can just do it intuitively without actually having to think about the law of total probability. And similarly, we have the general forms of Bayes theorem, which is we can rewrite Bayes theorem where if you have the probability of AI given B, we know this to be the probability of AI intersect B over the probability of B. And to find the probability of B, we had to do all of those intersections added together. Or if you're doing conditional probabilities, you do AI times the probability of B given AI, because that's the same thing as the intersection of AI given B. And the probability of B is you had to add all of those together. So in this next example, we're going to do one, again, but we're going to use the tree diagram. And this does only still have 2 events, but you could do it with more than 2 events. You just do the exact same thing that we've been doing. So we have a construction company employs several welders who do thousands of welds every year. From previous records, the company knows that 5% of all welds do not meet the industry standards. So that would be defective. And so they have to go through and inspect every weld. The inspector's performance has also been observed. So sometimes they'll classify something as defective, but it's really not. Or they might not classify as defective, but it really is, etc. And so they know things like any weld that is in fact defective will be correctly classified as defective, CD, by the inspector 96% of the time. Or in other words, they just tell us the probability of it being classified as defective, if it is defective, is 0.96. The rest of the time is classified as being good, CG. Any weld that is good will be incorrectly classified as defective 2% of the time. So we're saying classified as defective, if it's really good, is 0.02. And we want to draw a tree diagram to represent all of our possible outcomes associated with the experiment of selecting a weld and the classification of the weld. So when you draw these trees, sometimes people ask me, how do I know which thing I start with? Like, do I start with the D and G or the CD and CG, etc.? Well, sometimes it doesn't matter, like if you're doing dependent events. But in this case, the natural state of affairs is something's either defective or good, and then it's classified. So it's either defective or good, okay, and then it's either classified as defective or classified as good. Classified defective, classified good. So let's go back up. What's the probability of it being defective? We didn't write that down yet, but the 5% of all welds are defective. So the probability of defective equals 0.05. So we have 0.05, 0.95. Now we said the probability of it being classified as defective, if it is defective, is 0.96. So that means if it is defective, it means go along the defective branch. Classified as defective is 0.96. Now what's this branch? They're always complements. So if this is 0.96, you do 1 minus 0.96 is 0.04. Now, if we know it's good, you start off with it being good, probability of CD given that it's good. So that means go along the good branch. Now the probability of it being classified defective is 0.02. And again, the two branches will always be complements, so 0.02 plus 0.98 gets us up to our 1. Now you find the probability of the intersection, so probability of D intersect CD is 0.05 times 0.96, which gives me 0.048. And find each one is 0.002, 0.019, and 0.931. Again, these are the probabilities of each intersection. And you find probabilities by multiplying along the branches. And notice what probabilities were on this second set of branches? It was the conditional probabilities. So now, part D2, if a randomly selected weld is classified by an inspector as being good, what is the probability that the weld is defective? So they want to know what's the probability that it's defective if it was classified as good. Well, anytime you want to find a conditional probability, start by writing out the definition or the formula. So conditional probabilities, you do the probability of the intersection divided by the probability of the given part, which is classified as good. Okay. So now we come back up. We need to find D and CG, or D intersect with CG. That would be this one right here. D intersect with CG is 0.002. But this is why we like tree diagrams, because nowhere in the problem did it tell you the probability of it being classified as good. You would have had to think really hard and do a bunch of tricky things to figure this out. But with our tree diagrams, it's easy. You want the probability of it being CG. Come back up here and just select everything that has a CG in it. This one has a CG. This one has a CG. Those are the only things that have CGs. So if you want the probability of the CG, you put in everything that had a CG on it. So the 0.002 and the 0.931. That's our law of total probability there. It says if you want to find the probability of CG, you add up every single intersection that has a CG in it. And so our final answer is 0.00214.